So this is the second exercise in this final BETTER Hackathon. We had one this morning. The thematic area covered this afternoon is hazards. So Andrea from ETHZ will introduce the exercise in the context of the projects.
Yeah. So can I start, Simon?
Yes. Can you confirm you can see my slides?
Yeah. Can you? Hello, everybody. Can you see my slides? I hope so. So good afternoon, and thank you very much for the interest about this hackathon. As Simon introduced, this is related to geohazards, and the reason is that ETHZ is involved in the BETTER project specifically for the geohazards context. I will give you a quick introduction about the BETTER project for the people that doesn't know what it's all about, so that you have a better idea of the framework. And afterwards, I will quickly go through the main goals of the exercise or hackathon, and afterwards you will receive some information from people of the IT support, so that you know there will be also some support for specific reasons and some organizational issues. So the BETTER project, you see here, the main objective is to develop a service layer that will help to deal with big data challenges, and specifically with Earth observation data challenges, and mostly related to the new Copernicus Earth observation data from the Sentinels, which are generating a large amount of data. And of course, the big issue is now to explore and exploit this data in a convenient manner. There are 6 partners in the project. Some partners are more related to the technical development, like Demos, Terra2, and the Fraunhofer Institute. And there are some partners that are called the challenge promoters. And you will see in a minute why this is, what is the role of the challenge promoters. And the challenge promoters internal to the BETTER project are WFP, SATSEN, and ETHZ. And then we have some external challenge promoters. And this is ranging from geophysical institutes to insurance companies, other universities. And this is basically completing also the floor of challenge promoters for different kind of problems that you might tackle with the Earth observation data. What is the main rationale of the BETTER project? So the challenge promoters, they promote some challenges that have to be set by the user communities. In this case, we will talk about the geohazards, as we said before. And from the challenge, we basically, we try to focus on a specific issue that we have by working with a large amount of data. And then we define what are the main products and the requirements, and afterwards this is implemented by the technical team, and we do the validation of the results, and maybe we adapt a little bit also what is our requirements, because after you get the results, you also maybe change a little bit the idea how to analyze this data. And afterwards, when we basically finalized the challenge, we go towards the definition of a pipeline. So a pipeline is basically then using this toolbox that has been developed to automatically and systematically produce results. Usually after a new satellite image is acquired, or this can be also on-demand tasks for specific issues. In the project, we defined 36 challenges, so were defined as a target, and we basically have most of them ready, and we have a lot of nice results. And the idea of the hackathon is both to present these results and also to share the ideas and to see how this data can be then used further. Going to the scope of the activity of ETHZ. So ETH is a university, and we do a lot of research and education. And in specifically myself, I'm working a lot with geohazards. So geohazards, for people that don't know, are processes that are affecting the surface and subsurface of the Earth. And in general, we define geohazards. So we include in this category earthquakes, volcanic activity, landslides, and land subsidence. So all related to basically ground. We usually investigate these geohazards with specific techniques that have been developed over the years. And of course, the EO data has taken a lot of importance in the last years, especially because of the availability of data. And now we are trying to use more and more Earth observation data to analyze at regional scales, but also very local scales. The goal is, of course, to try to understand better physical processes, or maybe to understand how to use this data for services that can be for the society. In this particular case, we will talk today about earthquakes. If you have then specific questions about the thematic, you can ask later for better clarification. But here I would like to take less time as possible so that you start directly on the hackathon. So you see that in this very nice animation of iris, earthquakes, usually they produce two typology of deformation. So one is called the static deformation, and this is what you see associated to the faulting. You can see fault traces, and I know you might remember some images of large earthquakes causing dramatic static and permanent deformation to the ground. And then the second process is a dynamic shaking. That this is what is causing a lot of devastation also far away from the fault. So these two processes are very important to understand the physical relationship of the fault plane with then the area that is affected by the earthquake. There are several techniques to study the co-seismic deformation and the dynamic deformation, but in general, in the last years, radar interferometry has been used a lot for monitoring the co-seismic deformation, so the static deformation. And of course, the shaking is measured through the seismic waves that are recorded by seismometers. So following the scheme of BETTER, so we had a challenge, and we wanted to produce a homogeneous catalog of earthquakes of co-seismic deformation associated with magnitudes larger than 5 by using Sentinel-1 data, so radar data, and producing co-seismic interferograms. So the Sentinel processing is basically triggered by the information that is retrieved from the USGS, which is doing a global monitoring of earthquakes, and especially for magnitude larger than 5. They produce a lot of information that is much more than just the location of the epicenter, but also what is called a shake map. Shake map is something that is providing you the intensity of shaking due to the instruments that have recorded this earthquake. So it's based on points that are the seismometers that are in an area. In some cases, you have a lot of instruments that are located, and then you can have a very good resolution. In all the areas, you have just few. And then you produce these kind of maps. And the co-seismic, so the static displacement, is instead generated through the radar interferometry on the Sentinel-1 images. And so now we have developed the pipeline. So every time there is a new earthquake with a magnitude larger than 5, automatically this is basically listening on the USGS pager and is automatically waiting for the next image to be acquired and then generating the co-seismic interferograms. You can imagine that going back till 2015 when Sentinel started to systematically acquire. So this is a lot of information, and we have a lot of earthquakes that have been basically mapped by using this approach. So we have a huge catalog, and now the idea is to explore this catalog. So this is just an example of what you can do by combining the co-seismic interferogram. So the fringes you see, these color fringes are showing the co-seismic deformation. So you can look at this as a contour map of the elevation. For people that are used to interferograms, is quite easy to read. So every fringe cycle is associated to an amount of centimeters of ground motion permanently affecting the ground. And then you see these contour lines, so these yellowish and orange contour lines. This is basically associated to the intensity, so the instrumental intensity that has been recorded by the instruments located in this area. And as you can see, you can basically also identify the epicenter. So this is the star that is in this map. By combining these two information, we can do some preliminary investigation of the two processes. This can be also related to the fact that we don't have a lot of monitoring points on the ground, and so the shape of the ground motion that you get from the intensity is different from what you get from the co-seismic interferograms. So you see there is a fold plane that has been automatically generated by USGS by relying only on the seismic instruments. But then if you try to match this fold plane with the deformation that has been recorded by Sentinel, there is a mismatch. So I would say that the fold plane is actually going through the area where you have the highest gradients of fringes. And that's the reason why already here you can see what is the usability of this data if you can generate a product that is combining both information. So the general idea of the hackathon is really to end up with a product that is in this direction. So combining the co-seismic deformation and the dynamic deformation measured by the instruments. This is exactly what is explained here. So we basically set this hackathon to challenge the participants to find a convenient and clever way to exploit the large amount of results that we have obtained now in the pipeline. Of course, you could manually select this information and use it in a GIS environment, but this would be not very ideal. So this would be basically a bottleneck in the exploitation of the data. So the idea is to systematically generate a new high-level product that is a map that is combining the information provided by the satellite radar interferometry, the static displacement, and the ground seismic sensor, the dynamic displacement. So the framework of this hackathon, so you see there is a link, and in a minute Gonzalo, that is basically doing the technical support for this hackathon, is going through the information that you have already received as a link, and probably you have already seen what's there. So the total time would be 4 hours for the hackathon. In the link here, in the GitHub link, there are some examples that are available to facilitate the startup, so that you understand how to basically load the data and to use the data that is being produced by the pipeline in BETTER, and also the USGS data that is available. We basically set 2 checkpoints. One is at 3 and one is at 4, so 15 and 16 Central European time for group discussion. And then we will have a final review of the hopefully results between 17 and 17:30. There will be a channel for specific discussions, so it's a Google Meet link where you can basically connect to have directly questions for the thematic to me and for the IT to Gonzalo. And so this is basically the introduction, and enjoy. So let's start doing some code now.
So it's very, very easy to build a working set. So you have some examples, the events you can use during this exercise, and the notebooks have already some examples to get you started. To get this started, it's very simple. You only need 4 steps. First, you clone the repository, and this is to use in Ubuntu, okay, this instruction. Then you go to the folder that was downloaded, you make a Docker compose build to do the Docker image. This may take some time, and finally Docker compose up, and you can access the notebooks through these 2 links for your local host. The purpose of this tutorial is not to show you how it's done. It's very easy. It's just to let you know that I'm here to help you, and if you need anything, just make a question or use the Google link for to talk with me or Andrea. Okay.